Our next speaker up is Dr. Nirmala Shenoy. Dr. Shenoy is professor of the School of Information at Golisano College of Computing and Information Sciences, based in Rochester at the Rochester Institute of Technology, which also happens to be a hotbed of optical technology as well, not just networking technology, for those that are in the optics business. She teaches advanced networking courses. Her research interests include investigating simple protocol solutions for challenging network problems. She's designed the mesh tree algorithm, which is a robust tree algorithm highly suited to dynamic network connectivity used both for wired as well as mobile ad hoc networks. The mesh tree algorithm, which has been adopted in protocols, provides fast recovery on network component failures, thus improving network loop avoidance and availability. A version of MTA was the foundation for IEEE standard 1910.1 for loop avoidance in switched networks. And her work, and what she's going to talk about here, is a version of this MTA to be used for the design of a very simple and efficient protocol for routing in Folded-Clos topologies for data center networks. Please welcome Dr. Shenoy.
Good morning, everybody. The last couple of days, I've been talking to a few people about my project. You know, as a professor, I can research and I can bring whatever research results that I have or the implementations of that only to a certain extent, but I do need an industry partner after that, and that's where I've been talking to quite a few of you. And after all those discussions, I thought I'll just preface my talk with a couple of points, just to, if I just start off on the research ideas, it'll be difficult for you to follow. So I thought I'm just going to preface it with a few points. And one of that is, as a researcher, I think routing solutions can be simplified considerably. If you look at our routing protocols today, we flood reachability and link state advertisements, to almost in link state advertisement to all routers. And if it is BGP, you flood the reachability information. But rather than trying to discover routes and establishing these routing paths in such a complex manner, I thought that we have very structured networks today. So why do we have to disseminate this information all over? Can we leverage these structures and do what is called as a path establishment? Now that is the foundation for many of my research, okay? So as a case study, what I'm going to be presenting to you today is applying this sort of a technique, a path establishment rather than a route discovery, for data center networks. And I happen to know, I research in networks, so I do know that data center networks is a very hot topic, has got several challenges and things like that. So I adopted for my study, what I'm going to be presenting today is based on a Folded-Clos topology. And I'm also going to give you some results of, the most popular protocol suite that you use on Folded-Clos topology data center networks is BGP and ECMP for load balancing. And then in some cases, it is good to use BFD because that speeds up failure detection. So that is the comparison that I'm going to be making. I'm going to be using this mesh tree algorithm in my protocol, and then this implementation that I'm talking about has been established on Fabric testbed. It's a national testbed. I'll be talking a little bit more about it. And the protocol, the mesh tree-based protocol, is coded in C. And we downloaded BGP from FRR routing, identical topologies, conducted some results, and I'm going to present them. Actually, I wanted to include a demo here, but unfortunately, there was some miscommunication, and I asked for only 45 minutes for my talk. I thought the demo would be separately arranged, but then they came and said, can you include it, embed it as a video link in your talk? And I didn't have much time. But I have the whole setup ready on Fabric Testbed. So at the end of this talk, if anybody is interested to see this in action, I can demo it to you. Okay? So what else do I have here? This solution that I'm going to be talking about is not IP-based. So the first thing that comes to the mind of everybody is, if it is not IP-based, how is it going to be backward compatible with IP and Ethernet, which is very, very important if you're going to be looking at deployment. I'm an applied researcher, so if I'm working on any research project, I always look at it from the perspective that this has to be deployed, this should be deployed at some time, so I'm taking all those into consideration. So though it is a non-IP based solution, it is backward compatible with IP and Ethernet, and I'll show it to you when I go through the presentation. Okay, I think let us start with that. So growth of data centers, I've been working in this topic for quite a few years now, and just an introduction. In a data center, you have thousands of servers per location, and that can be extended to multiple locations. The data center network, which is the focus of my project or research work, is the backbone that connects all these servers in the data center. So it plays a crucial role in data centers. Okay, so if you, like I said, I've been researching in this topic and I've collected hundreds of articles on work that has been done on DCN architectures and topology, and it still continues. Okay, so besides the design challenges, the performance requirement challenges, there is this growing energy and carbon footprint concerns with data centers. I don't know how many of you have heard where they are submerging what they call as micro data centers in oceans to handle the cooling and things like that. And if you look at the RFC 7938, which is the BGP adapted to work on data center network, they do talk about operational and capital expenditure cost. Okay, so there are numerous challenges here. Okay, not that I'm going to be addressing all the challenges. Okay, so high maintenance, troubleshooting efforts, data centers can be really huge. So trying to maintain them and troubleshoot if anything goes wrong, plus the cost. The equipment cost, that is something which this research project can cut down considerably. The research cost, the energy, carbon footprint, all those can be considerably cut down with the proposed solution. And there are numerous other challenges, okay? So for our test, like I said, we adopted the Folded-Clos Topology, the most popular topology used in data center networks. And how do we simplify the protocol in a Folded-Clos Topology DCN? That is my research question. Okay, so protocols for data center networks, again, going back to all the research that I did, there are numerous protocol suites that have been investigated out there. The most popular of that is BGP based, okay? Minimally, in a data center network, you need a routing protocol, and because Folded-Clos topology has got a heavy connectivity, highly connected network, it is beneficial to use a load balancing protocol, and also you can quickly fall back to another path in the event a main path fails. And last but not the least is a protocol that can, a protocol that can speed up failure detection. Okay, because if that contributes to downtime and impacts network availability. Okay, so the popular protocol suite, I already mentioned this, is Border Gateway Protocol for routing, ECMP for load balancing, BFD for speeding up failure detection, and BGP requires TCP for its operation. BFD requires UDP for its operation. Now you throw all these protocols on top of a data DCN router. All these protocols have to work with one another, increased operational complexity, increased configurational need, troubleshooting, management, etc. The configurational needs at the end of this presentation, I'll just capture the configurational needs for the mesh tree-based protocol and if you are going to be running this protocol suite. Okay, increased energy, cooling, etc. So, routing in a DCN, like I said, as a researcher and a professor, I have the liberty to research in whatever I feel like, right? So I decided to adopt a new approach to route traffic between servers in a data center. And if you look at a data center, typically, especially the Folded-Clos, all that you need is how to reach the server networks. That is the only information you need to route, okay? You don't need all the paths between every router, and things like that. That doesn't have to be disseminated at all. Okay? And only thing besides the identifying paths to the servers is you should be able to store multiple paths in case a path fails, you want a quick fallback or failover. Currently, we disseminate this network information to all routers, but the latest BGP for DCN as per RFC 7938 actually does not do that. It's much more optimized and it just disseminates only the server network addresses. Okay. So that is the name of the protocol that we designed, multi-route mesh tree protocol, and I have a reason why I named it. And during introduction, they mentioned about this mesh tree algorithm, which I've been working on. Okay, and so what this MR-MTP does is it uses the structure of the Folded-Clos topology to simplify routing considerably. That's the way I can put it. You will see that as I present some results to you. And it also establishes, it establishes all loop-free paths from the TORs that connect your servers to the top-tier spines. All top-tier spines. Trees start at the TOR. So every TOR is a tree root, and you have the tree originating from the TOR to all the spines, and this tree from the different TORs, they mesh. And that's where you're able to establish all the paths. So this, I'll just continue to use the acronym from now on. MR-MTP establishes all routes from the TORs to top-tier spines. How is it possible to simplify this operation rather than using IP addresses? Why do I need IP addresses for routers? That's the basic question that I ask, okay? So we use what is called as virtual IDs, and those virtual IDs are enough to set up the paths, okay? Virtual IDs are auto-assigned. No configuration needed. You don't have to sit in front of a MR-MTP router and do all the configurations because the VIDs which are used for routing are all auto-assigned. MR-MTP, by the way, it unifies routing, load balancing, and fast failure detection. All the essential operations, I have unified it into a single protocol. And also, I'm not running IP in the routers. So when the packets from the servers arrive, the IP packets from the servers arrive, MR-MTP encapsulates, and using the VIDs, it forwards it to the destination server. Okay. It is independent of layer 3. It is layer 3 agnostic. We have all this confusion, IPv4, IPv6, etc., right? This one is completely layer 3 address independent. I can use IPv4 for my server addresses, IPv6 or any other address for that matter. It'll work. MR-MTP, obviously, by now you would have realized that it's its own protocol and it uses its own header. I'll introduce a couple of them later, not every one of them, okay? It is backward compatible to Ethernet and IP. It carries IP packets. You can deploy it along with IP. Turn it off if you don't want to use it. Turn it on if you want it to get effective. MR-MTP messages are carried in Ethernet headers. We sort of temporarily assigned one of the unused type field in the Ethernet header to identify MR-MTP. The protocol stack, if you look at MR-MTP, it replaces 6 different protocols that you use on DCN routers today, and that is the picture. I'm not exaggerating. That is exactly what you would be doing. So you see I had a pointer somewhere. Oh, there it is. I'm sorry, I can point only on one side, those who are on the other side. I hope it's not going to be very difficult. So you see on top of your Ethernet or layer 2 protocol, that is MR-MTP running at layer 3. You don't need TCP, you don't need UDP, no other protocols. All the essential functions for DCN operations are supported by MR-MTP. And here is what we currently use. Look at that. You're going to be replacing all that with this simple single protocol. So how much of reduction in configurations, operational complexity, costs, etc., that is something I've not yet studied. Okay. The benefits can be multifold, not yet investigated. So MR-MTP features and configuration needs. The only information that you need to configure in an MR-MTP router is the tier in which it is sitting. Because if you're using a Folded-Clos topology, you have tiers of spines, and then the TOR is the one that connects the servers. Okay? So TORs at tier 1 and spines at tier 2, tier 3, etc. TORs need a virtual ID, and even that we auto-derive today. Okay, even that does not require a configuration. Okay. MR-MTP code, believe it or not, it is just 40 kilobytes executable. We have coded it in C code, and it is available in that GitHub link. My students, set up all these fanciful things, and like I said, I currently have an implementation on the Fabric testbed, and the Fabric testbed actually uses Jupyter notebooks, and we have all the scripts available there. So you can just download it. You need an account in Fabric. I think anybody can get it easily, and you can test it out. We have the scripts to run BGP with the DCN version, and we have the scripts to run MR-MTP, and MR-MTP source code is also available for you. And like I said, the nice thing from a deployment perspective is MR-MTP can be turned off. They are operating in parallel. You turn off MR-MTP, you will fall back to IP-BGP. So, and I'm hoping that will help in incremental deployment. And if I'm running MR-MTP in one DCN location, I can easily communicate with another DCN location that's running the traditional protocols. So here comes the picture. I've been trying my best to see if I can simplify it. So that is a 3-tier Folded-Clos topology. And if you see here, those are the TORs. Route 1, Route 2, Route 3, Route 4, and I have one pod there, another pod here, and this picture is there only to explain the concept of mesh trees for you. I said every TOR is a tree root, and just look at that. That is the purple tree growing from TOR 1, and look at the branches. It just goes up and reaches all the top tier spines. I'm showing a partial green tree from route 2 and another partial blue tree from route 4. I did not put everything there so the picture doesn't get cluttered up, okay? So TORs are the roots of my mesh trees, and I call them the mesh trees because if you see all these different trees, different colored trees, they mesh at all the spines. So I have all the possible paths established. Okay, so I'll go through that quickly. All trees mesh at upper tier spines, I have covered that. The mesh trees, I think I've covered everything in my explanation. Okay. Now, how to implement this? If I'm going to be establishing all these trees, that is going to be pretty complex, right? But it's not. Okay, so here this is going to be an animation. If you miss any step of it, it's going to be confusing to follow. So just follow along with me. And what you see here is the TARs have got a VIDs now, a virtual ID. All the path establishment is done using virtual IDs, right? So the TARs here, you notice I have color coded them so you can follow them up easily. This is VID 11, 12, 13, 14. Very simple algorithm. We have also investigated other complex algorithms, which I won't be covering today. But this VID 11 is just taken from the third byte of the subnet IP address. So that is one rack. This is another rack. So I'm using an addressing scheme where it's very convenient for me. Other schemes are possible, so don't think that this is a limitation, okay? So that is the first step where I have these VIDs for the TARs, and here goes my animation. So TARs have assigned VIDs, okay, 11, 12, 13, and 14, and then the TARs will advertise their VIDs, right? So you see the advertisement going out on the 2 ports there, and spine S11, S12 get the VID and they say, hey, I want to join you. So the TARs will assign, oh, sorry, okay. I'm struggling with the pointer and the clicker here. So the TAR will assign a VID 11.1 to S11 because he'll take his VID, append the port on which he got the request and assign it to S11. And similarly, he will do it to S12. So you see these 2 spines have got unique VIDs now. That's how you establish unique paths, right? And then going to the next slide now, the spine S11, let's focus only on S11 for the timing, right? The spine S11 will now advertise his VID 11.1 and so it is being advertised to S21 and S23. S21, S23 will send in a request saying, I would like to join your tree branch or your tree. And then S11 will then assign, his VID appended by the port number on which the request came, 11.1, and then 11.1.2. It's as simple as that, done. No route discovery, nothing, and all the paths are established. All the TARs will send out their advertisement, and I use what is called as a, all these routers are point to point, okay? So there is a request acknowledgement sort of thing, so I don't need TCP or any other protocol to guarantee delivery, okay? So to derive a unique VID, I already gave you one strategy here. There are other schemes. We have investigated other schemes as well, but I won't be covering it now. I can discuss it with anybody who is interested. Okay, so the virtual IDs maintain the routing paths, the established routes, and if you see again, I have color-coded the purple tree going all the way up there, and the purple tree reaches every top-tier spine. So does the green tree. I have not put in the VIDs at every spine because it clutters the picture. And the only information I need is on which port the VID was acquired. That is the routing information I need. And believe it or not, that is my routing table. You can compare it with routing tables populated by OSPF and BGP and you'll know the difference. In fact, I'm going to show you one later on, okay? So, spines store the acquired VIDs and ports of acquisition. All routing paths are established using simple virtual IDs, okay? No routing protocols. no router network reachability dissemination to everybody in the network, no IP addresses to networks or devices, minimal configuration needed here. Okay, the only configuration required is I have to tell these devices you are tier 1, you are tier 2, etc., and that's it. Okay, well, now the next challenge comes. How do you forward an IP packet now? Okay, because none of these guys talk IP except the Tor at the point where he is connecting to the server racks. Okay, so let us follow the path of a IP packet forwarding now. Okay, so the IP packet is arriving from 1011 and it's destined to 1013. Okay, so IP packet arrives at Tor 11. The source is 1011, destination is 1013. So the Tor encapsulates this whole IP packet with a source VID, which is going to be 11, and from the destination VID he can derive the destination IP address, he can derive the destination VID. So he will encapsulate the whole IP packet in an MR-MTP header, source VID, destination VID. And from there, MR-MTP forwarding is done entirely based on these VIDs. Okay? So Tor checks his VID table. Okay, he doesn't have any entry for destination VID 13, but guess what? My parent, who is upstream, he has got more knowledge, so I will by default send it to either S11 or S12 after implementing a simple hash algorithm which we pulled out of the internet, and that does the load balancing for me. Very simplistic at this point in time. Okay, so it is, let us assume it is sending it to S11 after doing the load balancing. So S11 will look at his routing table, no entries for destination VID 13, so he will send it to his upper tier, again after doing a hashing, load balancing, and the packet then reaches S21. Okay, S21 looks at his routing table, VID table, and there he has 13 at port number 2. So he will then forward it to S13. S13 will check his VID table. 13 is here. I forgot to put the port number. So he will then forward it to Tor VID 13, and Tor will look at the destination VID, and he knows that it has reached the destination. He will de-encapsulate, remove the MR-MTP header and deliver the packet to the server. That's it. That is MR-MTP operation for you. Okay? And the nice thing, there's a security study we would like to do, and Bill Stackpole, my colleague who works in this project with me, he could not make it this time. He's from the security department, cyber security department, and we are looking at different mechanisms of securing this data center network. One of them is I can encrypt the whole IP packet along with the IP address. I don't need IPsec or anything. And the only header you will see is the MR-MTP source destination VID, and that is the only information I need to route. Okay. So we have a few other new concepts that we introduce. One of them is how to improve availability. To improve availability, I have to reduce the failure detection time. Okay, so for that purpose, we adopted this quick to detect, slow to accept. This is the reverse of your failure detection typically. Okay, so what do we do here? All MR-MTP messages are keep alive. I don't have to use a specific hello message because every message that is being sent between these routers has an MR-MTP header, and that is an indication that the router at the other end of the point-to-point connection is alive. I don't need a special hello message, right? So all MR-MTP messages are keep alive. And if there are no MR-MTP messages for the duration of a hello timer, then I'll send just a 1 byte, just a code there that says, hey, I'm alive. That's enough for me. Okay. So this is our hello message. Okay. It's a working protocol header, by the way. Okay. And that is quick to detect. Okay, sorry, I got confused a bit here. So I do not wait to miss 3 hello messages to declare that my neighbor is down. If I don't hear any messages from him for 1.5 hello timer, I will assume he is down. This is what I call the quick to detect. So the next question is going to be, so how are you going to do route dampening, right? So for route dampening, we use the slow to accept. That is, I have reversed the whole process here, okay? I'm going to use the slow to accept here. And after I have a failed neighbor, I have to receive 3 consecutive messages from him before I declare that he is up. And that takes care of all the route flapping, route dampening, etc. that I need to do. And that is what I call as slow to accept. And the dissemination messages, I'm going to show it to you later. It's a very tiny message that says, this VID is not accessible on this port on which you're receiving the message. That is my update message. Unlike with BGP, you have a whole packet of update data that you send to everybody. Okay, so this is a very generalized MR-MTP header to update, add a VID, delete a VID from a particular port. That is the generalized version of that. And on receiving an update, the only information change is this VID is not accessible on this port. No routing table updates. Very low control head. You will be surprised at the control heads we get. So what did we use? We used, okay, I have some time. We used a 4-pod test topology. When you're working on these test beds, it gets difficult to reserve resources. I'm literally, every node that you see there in the 4-pod test topology, every node is a virtual machine that is reserved somewhere where you have, I'm going to be talking about Fabric later, you have it reserved somewhere and then you get them connected and you set up your test topology. So trying to even set up 4 pods, reserve resources for 4 pods and testing takes quite a bit of time. Okay, so that is the maximum that we could test out. We are planning to move to mininet and then try to scale. And there were some friends of mine from Rochester who said that they have some local test beds which we are planning to check it out. Okay, so for the comparison, we use BGP, ECMP, BFD. And BGP, the version that we are presenting here is eBGP modified with the AS numbers to work on DCN. At that time, when we were originally testing it on the Genie testbed, that's an older testbed, it's deactivated now. We could not get the BGP DCN version from FRR routing to work. And hence, we had to go for the old eBGP, modify the AS numbers, and deploy it on these. The later BGP for DCN is much more optimized, and I have some results on that also if somebody is interested. And we also use BFD. BFD makes a significant difference, especially when there's a link failure and recovery. The loss of packets is considerably reduced if you use BFD. And of course, ECMP comes along with BGP and IP for, okay. Okay. Currently, like I said, I have this deployed. So the one that I have deployed on Fabric is this version, which is a much more optimized BGP version. So trying to summarize it before I explain my results, MR-MTP operates on Ethernet. I can even show you some captures, Wireshark captures, where you see all our messages being carried. We don't have drivers that interpret the information that is MR-MTP information that's carried in the Ethernet header, but otherwise you can see all the information there, okay? I think I have covered all this. Heavy reduction in operational complexity. Just compare the operations that I just explained to you with what you do with BGP, etc. Okay, backward compatible, communicate. I think I've covered all this. I've covered this also. You can turn off MR-MTP if you don't want it and fall back to the typical other protocols. Okay, so this is the test topology, and the reason I got a pointer is what we try to do is I'm going to quickly explain it to you. This is the 4-pod test topology, and we actually connected only one server. Again, problem with the resource reservation. We introduced failures at these green dots, TC1, TC2, TC3, TC4. And the performance impact of these failures changes. And then what we did is we sent traffic from this server to this server, failed all this, collected some results, and then we sent the traffic from here to the other side and collected some more results because they all make a difference, okay? So that is the convergence time. The convergence time that we calculate, we collect all the routing tables from all the routers and find out when they actually stabilize. So this is where our Fabric scripts come in. We do all the logging of all the BGP operations, collect all those files, and then go through them and then get these results. So if you see here, that is BGP for you. That is the convergence time in milliseconds. And this is the convergence time with MR-MTP, okay? So the convergence time with BGP was around 140 to 220 milliseconds. We had used BFD. We had reduced BFD. I think the transmit interval was 100 milliseconds. We could not reduce it anything below that because of false failures. But MR-MTP, we could cut down the hello timer considerably. And remember, failure detection happens in 1.5 times of hello timer, okay? And the MR-MTP, probably the most impressive thing here is you see that this is so very stable wherever the failure happens, okay? And like I said, there were VM limitations, the virtual machine limitations, and so we tried to locate sites that gave us very consistent results and good downtimes, and otherwise we were getting these false failures. And that is the control overhead, that is in bytes, okay, for the 4 test cases. Again, worth noting is the BGP. Now, unfortunately, this BGP is the original BGP, so the control overhead is a little bit higher. With the optimized BGP for DCN based on RFC 7938, this is considerably reduced, okay? So you see that it goes up to 5,000 bytes here, and this thing, again, probably the most impressive result here, observation here, is how it is consistently low, okay? It's not just going up and down. So that is a BGP update message on a failure that we captured, and you can have a look at all the, I mean, you don't have to know what exactly is there, but so many update messages, update information is included in the message. So this is the packet loss for traffic from network 11 to network 18 for those 4 failures. Worth noting here is how BGP has a very quick recovery when you fail at TC1 and TC3, but how the performance is heavily impacted when you fail at TC2 and TC4, right? So I'm just pulling out some numbers so you can see that clearly, okay? Again, for MR-MTP, the packets lost was less than 5. I'm going to skip this. I have 6 minutes more. Okay. So I'm just imagine the impact of this when you scale the network. Data center networks are supposed to be huge, okay? For a 4-pod, this is the impact. When you increase the network size, what will be the impact? And that is the packet loss failure when you're sending traffic from 18 to 11. Okay, if I get the time, I'll go back and explain why you see the difference here. Again, worth noting is the consistent low, or very stable value for MR-MTP as compared to BGP. So I'm pulling out some of those values there. And for MR-MTP, we had only 5 to 6 packet loss. I can actually demonstrate this and show it to anybody who is interested. And this is the blast radius, that is the routers that updated their routing table, which is very important because that tells you how stable the protocol itself is, because when you're changing the routing tables, it introduces instability. Your packets can be lost, misdirected, duplicated, etc., and that's not a good performance. So future work, there's quite a lot that we would love to do, but like I said, as a research professor working in a university, I'm limited to where I can take this, and that's where I'm seeking industry partnership here. We would like to scale the Folded-Clos topology to multiple spines. The last that I heard is you can go up to 6 spine tiers. If you want to go beyond that, the protocol will work easily. It'll scale easily. There's no scalability problem here. Okay? The timers, what you're seeing currently, they can be better tuned. We were constrained by the VM processing capacity limitations. So we would like to see how much we can reduce these timers, etc. Okay, and we would like to conduct some more extended failure test cases. That should not be difficult for us to do. More traffic in the network, which is something we'll do in the future. Traffic from multiple servers going to multiple other servers literally overload the network with traffic. And then this one we have already worked. Rather than trying to use a byte in the subnet IP address, we are trying to derive a VID using an algorithm and a seed. But that way, even if anybody sniffs an MR-MTP packet, he cannot identify the IP addresses of the servers from the virtual IDs. Encrypt IP packets originating from servers. And one thing we have been asking ourselves, and that's where Bill and myself, we are going to be working on it. I have a data center network here which is not running IP, TCP, BGP. That, I think, is a significant security improvement, because you cannot, none of those attacks that you can launch on these protocols, you can launch on a data center network that's running MR-MTP, because MR-MTP routers will knock off any such packets. Okay? But that is a study we are planning to continue, I and my colleague Bill. Impact on energy. Like I said, you have 6 protocols, and I have just a tiny little protocol running here doing all the operations that you want in a much more efficient manner. So what will be the impact on energy consumption, carbon footprint, CPU, memory utilization? And I think I can go on that. Okay? Impact on cost and investment. So if you're looking at a router that is just having one layer on top of Ethernet, I'm sure the cost of that router will be considerably less than trying to run a router with BGP, ECMP, BFD, etc. And like I said, I'm very much interested because I'm an applied researcher. I love to work in applied research, and I would like to see this, sometime deployed. Okay, now the demo on Fabric, like I said, unfortunately, some miscommunication. I should have followed up, which I did not do. So I'm not able to show you a demo here, but it is ready in my machine, and anybody who wants to check it out can do that. But I did capture a little bit about Fabric because, how do I say, the fact that we have really tested this out depends on how good the Fabric testbed is, and it's a great testbed, okay? So that is the definition of it. I pulled it from their website. It is an international infrastructure. It's deployed in multiple locations in the US, in the national labs, university campuses, etc. They have dedicated resources for this purpose, and those are the 29 Fabric websites. You can do different types of tests. It is funded by NSF. It has been extended to Asia and Europe as well. And that is a testbed of the locations, Fabric testbed locations in the US only. Okay? So the reason why it takes time is you have to reserve the virtual machines, you have to set up the topology, you have to set up these virtual machines with the desired operating system. You have to upload the code, whether it's MR-MTP or BGP code. All that has to be uploaded, and then you run the experiment. You collect all the log files, go through the log files, and then collect the results. So that's where it takes time. But we have scripts for all that. Only thing is, it just takes time. So again, like I said, the results that we presented were from the Genie testbed. We have results from Fabric, and I have results based on the optimized BGP for DCN version as well. So here comes some pictures that I pulled out from our Fabric testbed. How much of configuration do you need? That is on a 4-pod topology. That is the running configuration at T1, your top tier spine. And this is all the configuration for all the routers, MR-MTP routers. And if you notice here, I'm just telling them, hey, you are in tier 1, tier 2, etc. And I'm identifying the server ports at the TORs because that is the port where they're going to expect IP packets. Any other port, if you get IP packet, they just get knocked off. Okay. So, and that is a routing table at a top tier router when you run BGP. And this is with the optimized BGP for DCN version, by the way. And that is the routing table for at a spine. Okay, look at the number of entries that you have here. And that is a routing table or VID table at a top tier MR-MTP DCN router. You do the math, you do the comparisons, okay? So what is the takeaway? Like I said, in my introduction also, I specifically stated that I do like to investigate solutions. I don't want to follow the normal thing, which everybody IP-based, it has to be IP-based. I don't think it is really necessary, given that you have so much, every network that we have out there, there is a structure associated with that. Okay, so we can rethink the way we do routing. So do we need routing protocols at all? I don't know what you would call MR-MTP. It just establishes routes. It's not going and discovering or disseminating information not based on our typical algorithms. Simple techniques can automatically establish all the routing paths. They can be auto-configured, etc., auto-assigned, auto-configured. You name it and you can have all the benefits. And the benefits of auto configuration, auto address assignment, one major problem we face with when you're configuring networks is human error. You don't have that here. Okay? Non-IP based solutions can be very efficient and at the same time be backward compatible with IP and Ethernet. You don't have to discard all those. You can still work in parallel and slowly transition to whatever technology you want. Better ways to cut down on cost, energy, like why do you submerge a DCN in the ocean? There are better ways to doing this, right? No BGP, TCP, IP. This is a study we do plan to we do plan to conduct, and that is what is the impact if you don't have all these protocols which are pretty vulnerable. Yesterday somebody mentioned about the FCC and BGP security, and Bill actually forwarded that link and information to me. So are we going to be scared about it? In the long run, somebody will sniff an MR-MTP packet and find out ways to attack MR-MTP routers. Yes, but look at it like this. This is a very simple protocol designed by us. You can introduce any kind of, what is the right word? Security measures, okay? So I can, like I said, we just took a hashing algorithm from the internet and used it, So anytime you want to make changes to this, you can, okay? You can strengthen it, you can study the attacks that are being made out there and strengthen the protocol. Thank you.
Dr. Shenoy, thank you so much. We are at time, but I will
I'm sorry
for a couple of questions in case
I'm sorry.
anybody has any questions here in the room. Again, this is all research. Hopefully sometime we'll see something real in a large test bed of thousands and thousands of switches.
I hope so.
Pods. But it's beautiful to see. Thank you so much, Dr. Shenoy. Thank you so much. Any remote questions? I got nothing, I guess, because my buddy left.
I do have remote questions.
Okay, Dr. Shenoy?
This is from Michael Brooks. He did not give his affiliation. He said, so suppose we have a virtual server in DC1 prod 1 that migrates to DC2 prod 2. How does MR-MTP handle repathing?
Okay, this virtual, the migration of virtual machines, as far as to the best of my knowledge, this is one implementation where we are assuming that the server's physical IP address is going to be at the, going to be encapsulating any traffic that's going to be going across the virtual machines, okay? So all that the TARs are going to be seeing is the physical IP address. There is this technology VXLAN. By the way, I should have acknowledged an RIT alumni, an old student of mine who works with Markley Group, and he works with AWS, and we spent a year trying to figure this out. And like I said, this is one use case where we are assuming VXLAN and VTEP is running between the server racks. Okay, so the virtual machine migration is going to be completely transparent to the outer IP address that is provided by the server's physical IP address.
Thank you.
Excellent.
I have a second question. Do we have time?
Yeah, go ahead.
This is from Matt Patark, unaffiliated. He says, wonderful talk. For load balancing, you mentioned using a simple hash, but you also said that the entire payload can be encrypted as MR-MTP, as MR-MTP doesn't look at it. If the payload is encrypted, how can you do hashed load balancing? Does it become simply per packet load balancing, resulting in a high risk of out-of-order packet delivery to the destination?
Great question. We have thought about it, and we have not yet figured out how we are going to do it. But the point was, if at all I'm going to be doing any load balancing, it has to be based on some of the fields in the IP packet. So I can, and what a load balancing algorithm does is it just gets you a value, and then you use how many interfaces do I have, and you sort of you do some kind of mod or whatever arithmetic, and you fit it into one of those interfaces. So that value can be predetermined at the TOR and can be carried out, carried further by MR-MTP headers. Great question. We have thought of it, not that we did not think about it. We have thought of it, not yet tested.
Thank you.
Thank you. Again, Dr. Shenoy, thank you so much.